Good morning. Good morning, good afternoon, good evening. This is Luis Rodriguez and from Plum Island. And first of all, I want to thank the organizing committee of GFRA for the invitation to be here and congratulate them on a great job organizing this virtual meeting. I'm very pleased to introduce Dr. Jonathan Arts, a veterinary pathologist with degrees in veterinary medicine, preventive medicine, and pathology. Dr. Arts has many talents, including being a classical violinist and three-dimensional chess player, which I haven't witnessed yet those talents, but I have witnessed his talent as an accomplished researcher over the last 15 years. And when he started working at Plum Island in 2006, there were many gaps in knowledge about the pathogenesis of foot and mouth disease and in its relevant hosts. And over the last 15 years, he has tackled and answered many of these questions, such as identifying in detail the primary site of viral replication, both in ruminants and in pigs. And with his research team, he developed relevant challenge models and multi-model technologies to characterize the virus-host interactions in great detail. More recently, he has characterized the mechanisms of viral persistence in ruminants, both under natural field conditions and in experimental conditions, and also the viral host mechanisms influencing this important feature of FMDV natural history. So I leave you with Dr. Arts, presentation. Thank you.
Hello, virtual Argentina, and greetings to FMDologists across the planet. My intention today is to describe about 50 years of FMD pathogenesis research at Plum Island in about 27 minutes. The Plum Island Animal Disease Center was established in 1954 in order to provide a biosecure location for work on transboundary animal diseases that were exotic to the United States, particularly foot and mouth disease, and since that time has been the only location in the United States where FMDV can be handled. However, in late 2023 or 2024, it is expected that Plum Island Animal Disease Center will be closed permanently. Transitions are already underway for relocation of the entire Plum Island mission to the National Bio and Agro Defense Facility, otherwise known as NBAF, which is expected to be fully operational and housing the Plum Island mission in late 2023. Given that this is likely to be the last GIFRA meeting during which there's an operational Plum Island, it seemed appropriate to provide a retrospective view of the pathogenesis studies on foot and mouth disease that have been conducted at Plum Island over the past 50 years, with the contents detailed herein for future posterity and reference. And with the preamble out of the way, we can charge towards talking about pathogenesis studies in cattle, with just one small digression, which is a brief mention of challenge systems. Now, my purpose here is to emphasize that for pathogenesis studies, appropriate challenge systems must be chosen and tailored to specific study objectives. At one extreme, the contact challenge systems are the closest simulation of natural infection, but they are costly and difficult to standardize. At the other extreme, needle inoculation methods are easily standardized, but they are poor representations of natural infections. And while they have great utility for vaccine studies, they really are not appropriate for drawing conclusions about pathogenesis. We have found over the years that the sweet spot between these two extremes are the simulated natural challenge methods, which provide near natural routes of infection and are highly standardizable. Specifically, in the current era, for pathogenesis work in cattle, we almost exclusively use the intranasopharyngeal inoculation, whereas in pigs, we almost exclusively use intraoropharyngeal inoculation. Now, onward to talking about primary infection in cattle. If you dig into the Plum Island archives, about the earliest mention you can find of investigation of primary sites of infection in cattle are studies from the 1970s and early 80s, usually including authors Suttmoller and or McVicker. And really the most important accomplishment of this era of work was the establishment of the pharynx as an important early detection site, presumably early replication site for FMDV in cattle. This figure on the right, you notice the timeline of 0 to 24 hours. They're showing us viral infection dynamics as determined by recovery of virus from oropharyngeal fluid for 3 distinct strains of FMDV. As we move into the 1980s, there was a shift in momentum towards investigating the possibility that infectious aerosols could lead to primary FMDV infection in the lungs of cattle. Trend continued into the 1990s with some studies by Corey Brown and colleagues which used in situ hybridization and ultimately determined that there were roles for both the soft palate, part of the nasopharynx, and the lung in the early phases of FMDV infection in cattle. And now we jump forward by about another 10 years and find a new team of investigators with names like Rodriguez and Pacheco and Arzt, who standardized an aerosol inoculation method and utilized some new tools for detection of FMDV, including high throughput real-time PCR and virus isolation, and some new techniques for multi-channel immunofluorescent microscopy for detection of FMDV in situ. So what these guys showed with their aerosol inoculation system and their highly thorough, highly granular detection systems for FMDV, that the earliest detectable infection of cattle with FMDV occurred in the nasopharyngeal epithelium. What we see here at just 6 hours after aerosol inoculation is red FMDV staining co-localizing with the green cytokeratin, indicating the strict epithelial tropism of FMDV for pharyngeal mucosal epithelial cells. However, these studies also showed a continuum of changes in the lungs. What we see here on the left at just 12 hours after infection, still in the pre-viremic phase, there is red FMDV staining of the green cytokeratin positive epithelial cells, the pulmonary pneumocytes being infected, and that infection progressing to the appearance on the right panel at 48 hours after infection during the viremic phase, with abundant FMDV positive green staining pulmonary pneumocytes forming this cavitary lesion, which is quite reminiscent of an FMDV vesicle. This leads back to the same quandary, the question as to the relative roles of the nasopharynx and the lungs as primary infection sites for FMDV in cattle. And if you're getting tired of hearing this, just hold on because an answer is forthcoming soon. So as the 2010s became the 2015s, and with the arrival of a new scientist at Plum Island, Dr. Carolina Stenfeldt, we did set off on some experiments that ultimately provided the answer to the lung versus pharynx quandary. Specifically, we developed the intranasopharyngeal inoculation system that you see in the lower left. We used that system to perform numerous studies, both acute phase as well as persistent phase studies of FMDV in cattle. But along the way, we also did some critical studies using pig-to-cow contact transmission, which ultimately validated the intranasopharyngeal system and gave us the answers that we were looking for regarding the lung. So before we look at the pig-to-cow studies, we'll take a quick look at what we found with the intranasopharyngeal or INP inoculation. After INP inoculation of FMDV, we found primary replication occurred in the nasopharyngeal mucosa, similar to what we had seen with the aerosol model. However, there was no indication of replication in the lungs during the pre-viremic phase. So the work that we did in the pig-to-cow contact transmission system was really important, both for validating the intranasopharyngeal inoculation system, but also for sorting out this matter of lung versus pharynx in primary infection. Specifically, what we found in the pig-to-cow system was that FMDV primary infection occurred in the same regions of the nasopharyngeal epithelium as we had seen in the intranasopharyngeal inoculation system and also in the aerosol inoculation system. However, unlike aerosol, there was no evidence in the pig-to-cow system of FMDV replication in the lungs of cows prior to the onset of viremia. It is on this basis, therefore, in considering the natural semblance of pig-to-cow contact transmission to natural infection and considering the similarities and differences from the other pathogenesis models, we consider pig-to-cow to be the definitive work on bovine FMDV primary infection. Specifically, on this basis, we are comfortable saying that primary infection of cattle with FMDV occurs in the nasopharyngeal mucosa. Furthermore, FMDV replication does occur in the lungs during the viremic phase, but should not be construed to be primary infection. Furthermore, and relevant for the subsequent sections of this talk, the pig-to-cow system also validates various aspects of our INP system for the examination of persistent infection. Specifically, persistent infection also occurs in the nasopharyngeal mucosa of cattle, and the high prevalence of FMD persistence that we saw with INP is similar in the pig-to-cow system, approximately 92% both in naive and in vaccinated cattle. So now for something completely different, we shall talk about persistent FMDV studies at PIATIC, a subject that some people have taken to referring to as the carrier conundrum. I've broken the discussion of persistent FMD into 4 distinct chapters, and we shall begin with Chapter 1, the early days. From approximately 1965 to 70, the same group of scientists I described earlier, including Suttmuller, McVicker, and others, were quite prolific in their investigation of the FMDV carrier state. These 3 papers I list on the right are just a small sampling of what they published. The bullets below are the highlights of what came from those works. For one, we got the slightly arbitrary definition of carriers being FMDV detection after 28 days. They established the prevalence of the carrier state under different conditions. They did viral dynamics and virus load of carriers. They did various transmission studies, which were essentially all negative with one notable exception. They indicated the importance of oropharyngeal fluid for the diagnosis of carriers, and they talked a lot about the advantages of using TTE treatment for virus isolation from carriers. So jumping ahead 35 years this time to get to Chapter 2, we land in 2006 and the start of what we'll call the Rodriguez-Pacheco ARTS studies. I use this table from this Pacheco et al. Paper as demonstration of our modest ambitions at the start. We have this long tissue list of tissues that we're screening from numerous animals that are in the carrier phase looking for FMDV. This large tissue list required development and optimization of high throughput real-time PCR and virus isolation. You look in the category nasopharynx here and see all these red numbers indicating real-time PCR positivity in the pharynx and VI positivity with the shaded cells. And lastly, I'll mention that in subsequent slides you will see some of the new microscopy techniques that we were developing during that time, which helped us to further categorize the carrier. So in this Chapter 2 era, we were developing new microscopy techniques to localize FMDV in carriers, and here I have an H&E stain section of nasopharynx from a carrier cow. I use this to demonstrate the microscopic anatomy and the complexity of the epithelium. So notice here this stratified squamous epithelium, which attenuates down towards a respiratory epithelium and then becomes this very low attenuated epithelium just in the region where this lymphoid follicle gets very close to the epithelial surface. Now, when we put a anti-FMDV antibody and do our multi-channel immunofluorescence, we see that in carriers, the FMDV positive cells always localize to this attenuated epithelium that overlies the lymphoid follicles. So I mentioned the term modest beginnings for Chapter 2, but sometime around 2013 we were able to secure a relatively large grant from DHS, which enabled us for the first time to start doing some prospective studies on FMDV persistence. So this entire project was centered on the concept of the carrier state divergence. Specifically what we mean by this is if you take a naive animal, challenge him with FMDV, follow him through clinical stage of infection, the animal gets to a divergence, at which point the animal either clears infection to become a non-carrier or terminator, or the animal fails to clear infection and becomes an FMDV carrier. So we were planning to characterize this carrier state divergence in various ways with the ultimate goal of understanding why some animals became carriers and others cleared infection. But the first task was to just identify when that divergence occurred. So here you have viral dynamics, non-vaccinated animals separated out by whether they become carriers or whether they become terminators. The main difference, of course, is this light blue line indicating detection of FMDV in oropharyngeal fluid in the animals in the carrier group. Now, when did this divergence occur? It turns out that we were able to correctly identify the carrier animals by oropharyngeal fluid detection in the range of 17 to 21 days. In that same time period, the animals that were destined to become terminators had already gone negative. Therefore, we determined that the divergence occurred in non-vaccinated animals before 21 days after infection. Now, when we bring in vaccinated animals, things look similar but different. First of all, the blue bars for lesion scores are gone because these animals were all protected from clinical FMD. The viral dynamics are blunted, but the distinction of the two cohorts is similar in that there is a group of carriers based upon detection of FMDV in oropharyngeal fluid, and there is a cohort of animals that do not become carriers, rather they clear infection. Now, if our carriers are defined by presence of FMDV out here at 28 days, we see that these animals could be identified as early as 7 to 10 days after infection consistently, that they diverged from the animals that were becoming terminators in this time period of 7 to 10 days. Our next job was to characterize the microscopic environment in which persistent infection was occurring. So we first localized FMDV to regions of nasopharyngeal mucosa. We co-localized the virus exclusively with cytokeratin, indicating the strict epithelial tropism of FMDV during the carrier state, and our next task was to detail the phenotypic characteristics of cells in the region of persistent infection and try to discern if there were differences between carriers and animals that had cleared infection. That work is detailed in this Stenfeld et al. Paper, but I don't have time to go into it at this time. And as one final note on microscopy, I want to point out that the localization of FMDV in vaccinated carriers and non-vaccinated carriers was entirely indiscernible. In both cases, the same quantities of cells were infected and they were in the same locations. The attenuated epithelium overlying malt follicles in the bovine nasopharyngeal mucosa. As I move towards Chapter 4, I realize there's no way I can cover any of these downstream ancillary persistent studies with any kind of detail, so instead you get them in bullet form with some paper references off to the right that you can follow up if you so choose. Chapter 4.1 is on the subject of host factors associated with the carrier state divergence. We have 3 papers on this subject at present, and somewhere within this GIFRA conference, Dr. James Zhu will be presenting the latest chapter on host factors associated with FMDV persistence. Chapter 4.2 required the advent of high-throughput next-generation sequencing for acquisition of full-length sequences of FMDV. Also required the arrival of a new postdoc evolutionary biologist named Dr. Ian Fish. With these pieces in place, we have characterized the carrier state divergence in the context of within-host evolution of FMDV at the consensus level as well as subconsensus levels. For Chapter 4.3, we actually had to go to another little island, this one called Lindholm in Denmark, where we collaborated with Dr. Graham Belsham on a unique study, the main output of which was the finding that if you collect oropharyngeal fluid from carrier cattle without adulteration, inoculate it into naive cattle by intranasopharyngeal deposition, it does in fact cause fulminant foot-and-mouth disease, thereby indicating the true infectiousness of OPF from carrier cattle. And our latest greatest creation, chapter 4.4, in which we show that carriers infected with serotype A virus, subsequently superinfected with serotype O virus, will give us back recombinant chimeric AO viruses just 10 days after superinfection. That work, hot off the presses and just recently published. And if you want to hear more about it, there are 2 additional talks on this subject within this GIFR conference, one by Dr. Carolina Stenfeldt and the other by Dr. Ian Fish. And so now we shall move on to FND pathogenesis in pigs per piatic for the people that prefer alliteration. There really is not much in the historical records from piatic in this category, with the exception of some studies from the 1990s by Corey Brown and colleagues that looked at early pathogenesis of pigs using in situ hybridization. Around 2012, we started doing some pathogenesis work in pigs, and our first intention was to characterize the primary sites of infection, to explore this conventional wisdom that pigs got infected by eating FMDV, whereas cattle got infected by breathing FMDV. So we developed 2 new simulated natural challenge methods, one being nasopharyngeal inoculation, same as we had done in cattle, and the other being oropharyngeal inoculation, in which the virus was deposited directly onto the tonsil of the soft palate. The short version of the output of these studies was that, in keeping with conventional wisdom, pigs did get infected through their oropharyngeal tonsils and not through their nasopharynx. So the primary sites of infection in pigs were identified as paraepiglottic tonsil and tonsil of the soft palate. What you see in this image is a section of a paraepiglottic tonsil in which the red FMDV staining co-localizes with the green cytokeratin, indicating strict epithelial tropism of FMDV for the tonsillar epithelium in these pigs. Another intention of this body of work was to address another piece of conventional wisdom about FMD in pigs, specifically that pigs are the great aerosolizers of FMDV. Our intention was to determine what anatomic location was responsible for generating all the FMDV that these pigs were aerosolizing. So we spent a lot of time dissecting a lot of respiratory tracts from a lot of pigs, with the expectation that at some level of the respiratory tree, whether it was lung, trachea, nasal cavity, we would find a site where there were very high loads of viral replication corresponding to the high levels of shedding and aerosolized virus that is known to come from pigs. However, we never found any such site. Rather, what we found was that during clinical FMD, when pigs were aerosolizing the highest quantities of virus, the greatest viral loads were found in the oropharyngeal tonsils. What you see here in this slide is a section of tonsillar epithelium with a very unique lesion, these microvesicles within the epithelium containing abundant FMDV positive cells. Therefore, our conclusion was that the high levels of aerosolized virus from pigs were coming from the tonsils and were being aerosolized via vocalization or respiration, even though the virus was not being generated within the respiratory tract. The last piece of pathogenesis work in pigs that I'll describe was pretty labor-intensive, although not very elegant. The purpose of this work was to address another piece of conventional wisdom, the idea that pigs were not able or not competent to be FMDV carriers. And for this purpose, we recruited pigs from various studies. We inoculated some pigs specifically for this study. We harvested a lot of tissues, and ultimately we did confirm the conventional wisdom that pigs were not competent to be carriers of FMDV. However, we were able to detect FMDV RNA and antigen in selected lymph nodes that drained vesicle sites for long periods of time after infection. However, the more important finding was that no viable virus could be isolated from these pigs. I'd like to spend just a couple minutes describing some pathogenesis-like studies that we've been able to execute with partners in endemic regions, particular partners in Vietnam and India. From studies in both India and Vietnam, we've been able to make some progress characterizing the sites of persistent FMDV infection in Asian buffalo, and found it to be more similar to cattle than it is to Cape buffalo. And in India, we happened to be at the right place at the right time in order to document some bovine abortions associated with FMD outbreaks, and we were able to localize FMDV to the soft palate of the aborted fetuses, which was an interesting novel finding that perhaps will get followed up another time. A few quick acknowledgments. First, within the ARS leadership, our research leader, Luis Rodriguez, and National Program Leader, Cyril Gay, for their dedication to basic science research, even in an applied science program. The MVP award goes to Carolina Stenfeld as collaborator and co-author of almost everything that I've showed today, and of course provider of all the prettiest images. Various contributors and postdocs over the years, the most noteworthy are Miranda Bertram, Ian Fish, Michael Eschbaumer, and Haley Crockett, and laboratory support from 4 critical players: George Smoliga, Ethan Hartwig, Stephen Pausick, and Lauren Holinka. With that, I'd be happy to take any questions or just enjoy the awkward remote silence. Thank you for your time and attention.
Thank you, Dr. Arts. So I guess I have a few questions that I have on the chat. One of them from Dr. Eschbaumer relates to the detection of FMDV antigen in persistently infected epithelium. It's always found in the superficial, most superficial layers. Do you have any thoughts on why that is?
Yeah, so short answer is no, I do not. Slightly longer answer is it's a very interesting question, something I've wondered about a lot, and something that we have explored in various ways, particularly trying to consider the possibility of differential phenotypes within the epithelium to define that tropism, not just for the superficial layer, but a similar but different question: why only these areas around the malt tissue? And so we've tried over the years different specific cytokeratins, different integrins, a lot of other types of phenotypic markers, none of them providing a specific answer. So Michael, I'm sorry, I do not have that answer for you, but let's check back in on that in another 5 years or so.
All right. So another question from the chat. So do pigs become persistently infected or not? I guess.
No, they do not. And so we did a pretty exhaustive study on that. I didn't give a lot of details, but I think there were 5 distinct strains of FMDV included in that study. And we carried those pigs, some of them as far out to 90 or maybe even 120 days, cut them up into lots of little pieces. And as I mentioned, there's no recovery of infectious virus from pigs in anywhere near to 28 days. The only RNA and antigen detection at later stages was in lymph nodes that were draining lesion sites. But again, short and important answer: pigs are not competent to be FMDV carriers.
Same question on small ruminants.
Okay, so what does Rebecca say? Small ruminant studies. Yeah, so I didn't have time to cover that. We did a little bit of work with sheep, and we found carrier sheep. The localization of the FMDV in the carrier phase was sort of in between what was reported previously for Cape buffalo and the cattle studies we have. From what I recall, we found some virus in tonsil and also some virus in the nasopharynx. And I would refer you to the paper it's one of the Stenfeld papers where we describe that in detail and show some pretty pictures.
All right. So a question, Don King and I were kind of thinking on the same track. So you have answered many of the questions regarding, or clarified many of the questions regarding persistence. What are the biggest questions that you see moving forward that we still need to address?
Well, so yeah, I think if you say pathology textbook, I would say, yeah, I couldn't imagine much more work in that area, with the exception of maybe confirming that some other serotypes and strains all do the same things as the strains that we've already looked at in the laboratory. And perhaps you could say, well, different genetic backgrounds of livestock, both cattle and other species that are susceptible to the carrier state. However, if you change that word pathology to pathogenesis, I think it's very clear that there is still a lot more to learn and investigate. And so that's what I was getting at with that 4.1, 4.2, all that ongoing work. I think there's still a lot that we need, a lot of gaps we need to fill. And host factors in persistence certainly being a critical aspect, because I think that probably is more of a host phenomenon than a virus specific phenomenon. And in the acute category, acute infection, I think getting back to the Eschbaumer question, understand why specific cells actually get infected and others do not. And the point there, why that has real world implications, I think as we move into next generations of vaccines, we can think about blocking specific virus-host interactions, and that could be a long-term goal of next-generation countermeasures.
Excellent. So we have a couple of other questions. Okay, I think you answered tropism regarding different serotypes and regarding not having that being serotype specific. Innate antiviral immunity and persistence, I guess, that's a question by Alejandra.
Yeah, so that's something that we keep scratching at and hoping and striving to get better at. So I think that was chapter 4.1 that we have published on host factors. And you mentioned innate specifically, and that surely is one of the categories that comes up, but there's more work in terms of bioinformatic analyses, but also those studies are really labor intensive, and generating the samples is really hard to have enough samples, to have enough confidence in the output. And so, yes, we have looked at that. I would refer you back to those papers from Stenfeld, from Eschbaumer, from Zhu that look at various host factors, but it definitely is an area that I would like to chase down further in the future, and in particular to use unbiased transcriptomic techniques like RNA-seq. And those are all things that we have in the pipeline, and hopefully we'll continue to improve at the output on that subject as well.
All right, we're coming to an end of our allotted time, so I want to encourage everyone to go back to the little gathering town thing that we have and pick your nice avatar and interact with each other there to answer some of the questions that are still on the chat. And thank you, Jonathan, for a great presentation. I really enjoyed it very much. Thank you.
Very welcome. Thank you.